This PowerPoint is over moment of inertia examples. So the first example here, it says that a constant torque of 20 Newton meters is applied to a grindstone, of which a moment of inertia is 0.125 kilograms meters squared to get it to spin. So calculate the angular acceleration. First off, we have the torque and we have the moment of inertia, so we can use the Newton's second law where net torque equals moment of inertia times angular acceleration. Plug in your numbers, divide the torque by the moment of inertia, and you get a total angular acceleration of 160 radians per second squared. All right, the next question says find the angular speed of the grindstone when it made an angular displacement of 45 radians. Okay, so we got final angular velocity is what we're looking for. So final angular velocity squared is going to be equal to the initial angular velocity squared. It says it starts from rest plus 2 times the angular acceleration, which we found to be 160, times the angular displacement, which is given to be 45 radians per second. So we go ahead and plug in our numbers, 2 times 60 times 45, and then we get 14,400, and we got to square root both sides in order to find our final angular velocity. We get 120 radians per second. The next question, it says a solid steel ball with a radius of 0.15 meters has a mass of 4.0 kilograms rolling down a 12-degree incline without sliding. So part A says, what is the linear acceleration of the ball down the incline? All right, so first off, we need to figure out a couple of things. We need to figure out the acceleration of the ball. We need to figure out the rotational acceleration because both of those accelerations are occurring at the same time. We have translational acceleration, which we're going to use Newton's second law linearly to find that acceleration, and then we have rotational acceleration, which we're going to use Newton's second law with torque. So let's start with the torque equation. We got net torque is going to be equal to the moment of inertia times angular acceleration. The torque is going to be caused by friction. Gravity is being applied at the center of gravity, or the center of mass, the axis of rotation, but the friction is going to be applied at this surface here. So that is what's causing it to rotate. Without friction, it would just go down without rotation. So that force of friction times the radius of the ball is going to be equal to kmr squared. That's the moment of inertia for any object, where k for a steel ball should be 2/3, I believe, 2/3. Then mr squared, and then we got the acceleration divided by radius. Because the outside is accelerating, then the linear acceleration on the edge is going to be equal to, if we divide that by radius, that gives us our angular acceleration. All right, so you notice here that the radius, because the force is being applied at the edge and the acceleration is at the edge, then these radii that they have are going to match the radius of the to find the moment of inertia. So that's actually going to cancel on both sides. So the radius of the ball is actually not needed. All right, so let's go ahead and clean up our equation. We got the force of friction is going to be equal to kma. Now, I don't really know enough here. I don't know the force of friction. I don't know the acceleration, so I've got too many unknowns. So I need to get another equation. So net force is going to be equal to mass times acceleration. The perpendicular component of gravity is going against friction. Friction's pushing up, gravity's pulling down, but it's only that perpendicular component. I'm sorry, the parallel component. So that's going to be the sine component. So mass times gravity times sine of the angle. That's going to be our parallel component. If we rearrange this, we take the force of friction over here, becomes positive, mass times acceleration over here becomes negative. And then that's basically all that we need here. We can go ahead and set these two equations equal to each other because we got both of them solved for force of friction. All right, so now that they're equal to each other, you'll notice that each term has a mass in there, so those masses will cancel. And then I'm left with k times a is going to be equal to g sine of theta minus a. So we get a on the same side because that's going to be the variable I'm looking for. We factor that out. We get k plus 1 times a is going to be equal to g times sine of theta. And then we divide both sides by that k plus 1. I was incorrect. It's actually 2/5 because we're dealing with a solid sphere. It's going to be a lower moment of inertia. 2/3 was a hollow sphere. So 2/5 with a solid sphere plus 1. We go ahead and solve that, and that gives us 0.14. And then the right side of the equation here, 9.8 times sine of 12 degrees, that gives us 2.04. We go ahead and take the 1.4 to the other side. We get our acceleration is going to be 1.46 meters per second squared. The next part here says, what's the minimum coefficient of friction between the ball and the ramp for the ball to not slide. All right, so first of all, you'll notice that I kept that force of friction equation that we derived on the previous slide, and we also found the acceleration, so I'm going to use that with this as well. So we get 2/5, which is the K value for the solid steel ball, times the mass, which is 4, times 1.46, and we get that the force of friction is going to be equal to 2.34. Now to get the coefficient of friction, I need to know the force of friction and the normal force. The normal force is going to be equal to the perpendicular component of gravity on the ramp, so that's going to be equal to mass times gravity times cosine of the angle, which is 12 degrees. So 4 times 9.8 times cosine of 12, that's going to give us 38.3. Now to find that minimum coefficient, we need to divide the force of friction by the normal force, and that gives us 0.061. So that's the minimum coefficient of friction needed, the minimum coefficient of static friction needed to get it to roll. If we have a friction that's less than this, which is actually pretty difficult because that's kind of low already, then that means the ball will actually start sliding. It may still roll, but it won't roll perfectly in sync with the linear velocity. It actually will slide as it goes down as well. Part C says, assuming that the ball started from rest, what's the final angular velocity of the ball after it's rolled 3 meters along the incline? Okay, so we can use kinematics with this because we have the mass, we have the distance that it travels, we have the acceleration, and we know that it starts from rest, so we can do final velocity squared equals initial velocity squared plus 2 times acceleration times displacement, plug in our numbers, then we get 2 times the acceleration, 1.46 times 3, that gives us 8.76. So to find our final velocity, we square root both sides, and we get a final velocity of 2.96 meters per second. Now to find the angular velocity, we could take that velocity, final velocity 2.96 divided by the radius, which is 0.15, and that gives us an angular velocity of 19.7 radians per second. The next problem, it says a weather vane consisting of a rooster sitting on top of an arrow is sitting on top of a garage. The vane is fixed to the vertical shaft of radius 0.18 meters that is free to rotate as shown in the figure below. A student sets up an experiment to measure the rotational inertia of the rooster and arrow. String is wound around the shaft, passes over the pulley, and then is connected to a 2 kilogram mass. So kind of what's going on here, we got the string going around there, and then over the pulley where the mass is hanging right there. The mass is released, and the student determines the acceleration of the mass is going to be 0.4 meters per second squared. So first off, what's the force of tension in the string? All right, so we set up our free body diagram for that little mass, and that gives us the force of tension upwards going to be pulling against the force of gravity downward, so net force is going to be equal to mass times acceleration. Now the acceleration is downward, so we're going to say that downward is going to be positive, so that means force of gravity minus tension is going to be equal to mass times acceleration. If we said that upward is positive, that's okay, we can do that, but then we'd have to make the acceleration negative on this side. So just for simplicity's sake, to make the force of gravity and acceleration positive, force of tension would be negative, and we go ahead and solve for our unknown, which is the force of tension. All right, so mass times gravity, we know what that is. We got the mass, which is 2 kilograms, times gravity, which is 9.8. We got the mass again, which is 2, and then the acceleration is 0.4. So we can go ahead and solve for our force of tension. We get a force of tension that's going to be equal to 18.8 newtons. So find the rotational inertia of the rooster and arrow. Now the force of tension is actually what is causing the rotation here. That's the force that's producing the torque. You got to be careful here because a lot of times when people see this problem, they'll say, well, the force of gravity here is pulling down, so that is going to be equal to the force of tension, and then we'd say the force of gravity would be equal to the torque, or would be equal to the force that's applied in creating torque. And that's actually incorrect because the force of gravity is not equal to the tension, and the tension is what's pulling on it. So with that being said, we can use that torque caused by the force of tension. So net torque is going to be equal to moment of inertia times angular acceleration. Now the force of tension that we found over here times the radius is going to be equal to the moment of inertia times, now we have acceleration divided by radius because the string is going to be accelerating, and that string is going around the outside of the shaft, which means that if we take that acceleration, that outside acceleration divided by the radius, that'll give us the angular acceleration of the object. Okay, so we go ahead and solve for a moment of inertia. We multiply both sides by radius, so that gives us radius squared times the force of tension, and then we divide by acceleration, plug in our numbers, 18.8 times 0.18 squared divided by 0.4, and we get the moment of inertia of the entire rooster as being 1.52 kilograms meters squared. This next question, it says two pulley wheels, one of radius 0.3 and the other of 1.4 meters, are mounted and clamped together on a common axle. So essentially we got two pulleys, but both of them are together, which means that as one rotates, the other rotates, and just like any two things stuck together, they'll rotate at the same rate. So the rotational inertia of the two pulleys together is 1.5 kilograms meters squared. An 18 kilogram mass is attached to the left end, so that's mass 1 over here, and then a 6 kilogram mass is over here going to be on the right end. Now what's interesting about this is because you have a larger mass for mass 1, but that larger mass has a smaller radius. And then we have mass 2 that has a larger radius, mass 2 being a smaller mass, so it's a smaller force of gravity. So we can go through and we could figure out, well, which one's going to be the bigger force of gravity, which one's going to be the bigger torque, but I'm just going to arbitrarily say that one of them is going to be positive, the other is going to be negative, and I'll let the math work out and tell me if I chose the right direction or not. All right, so we got, for this mass over here, we got force of tension 1 upward and then force of gravity 1 downward, but it is going to accelerate downward. Because it is it's a smaller or a larger mass, so we assume it's going to accelerate downward. And if I'm wrong on that, then when I actually find my acceleration, then it's going to be it'll be negative. It'll be opposite of what I expect it to be. All right, so force of gravity 1, since acceleration is assumed to be downward, then that means we're going to make force of gravity downward, and everything's going to be positive downward. So force of gravity 1 minus force of tension 1 is going to be equal to mass 1 times acceleration. We kind of rearrange this equation, plug in our numbers with 18 times 9.8. And then we get 176.4 minus the force of tension equals 18 times acceleration. All right, so that's about as far as we can get on that. If we solve for the force of tension, we get everything else on the other side. But you'll notice we can't really solve that because we don't know what the acceleration is. All right, so we're going to do the same thing with the other mass. The other mass has a force of tension up and a force of gravity down. Now, if we say that gravity 1, if we say mass 1 is downward, then that means we'd have to say mass 2 is upward. Now, as long as you're consistent with your math, the math will work out. And if you get a negative at the end with your acceleration, that'll tell you just chose the wrong direction, but that's okay. Mathematically, it'll work out. So consistently, we have to say that the mass 2 is accelerating upward. All right, so force of tension 2 minus force of gravity 2 is going to be equal to mass times acceleration. We go ahead and plug in our numbers, and we get that the weight of mass 2 is 6 times 9.8, 58.8. We take that to the other side, and we get our force of tension 2 equation is going to be equal to 58.8 plus 6 times acceleration. All right, so that gives us our two free body diagrams for the hanging masses. Now we need to figure out what's happening with the rotation of the pulley itself. And with that being said, basically what we get is we get a force of tension 1 that is causing a counterclockwise rotation, and then force of tension 2 that's causing a clockwise rotation. So we're going to add those together, those torques together, and see what the angular acceleration is. So we got our two equations. We'll go ahead and solve for the, we're going to basically make the acceleration, since we're going to be looking for angular acceleration, then linear acceleration is going to be equal to the angular acceleration times the radius. Now, radius 1 is 0.3, radius 2 is 1.4, so we plug those numbers in, and we get our force of tensions with respect to the angular acceleration. So with those two equations, we now have net torque is going to be equal to moment of inertia times angular acceleration. All right, so the two force of tensions, again, we said that mass 1 is going to be accelerating downward, mass 2 is going to be accelerating upward, so we're saying that this whole thing is going to be rotating counterclockwise. And that means that force of tension 1 produces a positive torque, and force of tension 2 produces a negative torque. And that's going to be equal to moment of inertia times angular acceleration. We go ahead and plug in our numbers. Now this gets really big, because now we have the total equation for force 1 plugged in here times its radius, minus the total equation for force 2 times its radius, and that's going to be equal to the moment of inertia given to us in the problem is 1.5 times angular acceleration. Now you'll notice this equation only has one unknown in it, and that is angular acceleration, which is what we want. But now we got to do a lot of algebra in order to get that angular acceleration isolated. So you distribute the 0.3 to both of these terms, you distribute the 1.4 to both of these terms, and that negative you got to distribute to both of these as well. So there's those two terms are going to be negative, and then these two terms right here, we got to positive minus that that right there. And then we're going to take the angular acceleration. We got a negative angular acceleration here, a negative angular acceleration there, and then we got the two values here, the 52.92 and minus 82.32. That gives us negative 29.4. And then those angular accelerations there, we combine those as well. We're going to take that to the other side, and that gives us a total of 14.88 times the angular acceleration on this side. Then we could divide both sides by the angular by 14.8 and get the angular acceleration negative 1.98 radians per second squared. All right, so right here you can see that I chose the wrong direction, that it actually is going to be rotating. It's going to be accelerating clockwise because I said it was going to accelerate counterclockwise, but you see that negative pops up, which means it's actually going to accelerate the other direction. That's okay. As long as you're consistent the whole way, the math will lead you to where it's going to where it's actually going to accelerate. So the next question, it says find the tension in the cord for the 18 kilogram mass. That's pretty straightforward. The force of tension for the 18 kilogram mass is going to be mass 1, so we use that equation. And then we plug in our number. It's going to be 176.4. Now, since we chose the wrong direction for the angular acceleration, then we still have to put that negative in there because we assumed, all of our math assumed that that was going to be a positive acceleration. And now we plug that in, we get a total of 187.1 newtons for force of tension 1. Now for force of tension 2, let's go ahead and plug in the numbers there, and you get the force of tension 2 is going to be 42.2 newtons for that. Next example, it says that 3 particles are located in a coordinate system shown in the figure. Find the distance of the center of gravity, or center of mass is another term for that, from the origin, given that mass at the origin is going to be 5 kilograms. Mass 1, which is in the x direction, is going to be 3 kilograms. Mass 2, which is in the y direction, is going to be 6.5 kilograms. And then we have the distance for 1 to be 3 meters and the distance for 2 to be 4.5 meters. All right, so to find our center of mass or center of gravity, we're going to take what's called the moment. The moment is referred to as the mass times the distance for each of those objects. Now, in the x direction, mass sub 0 and mass sub 2 have 0 lever arm. They have 0 lever arm. So essentially, the only moment there's going to be is going to be mass 1 times its distance. So mass 1 times its distance. All right, so the mass 0, x0, and mass 2, x2, those will actually cancel to give me 0. So it's just going to be the 3 times 3 here. And then we divide by the total mass of the system. So that's 9 over 14.5, and we get 0.62 meters. Now for the y direction, we're going to do the exact same thing, but you see that mass sub 0 and mass sub 1 have 0 lever arms, so it's only mass 2. So we go ahead and plug in, use the same equation where the total moments divided by the total mass is going to be equal to the location of the center of mass. And you see that the object at the center is going to have 0 moment, mass 1 has 0 moment, and then mass 2 is going to be 6.5 times 4.5. We divide by the total mass of the system. It's going to be 29.25 divided by 14.5, and we get 2.02 meters. Now that gives us the x position for the center of mass, and that gives us the y position for the center of mass. And now it's asking for the distance of the center of mass from the origin. So with that, essentially what we're going to do is we're going to take the x component, we're going to take the y component, we're going to make a right triangle out of it, and the distance is going to be the hypotenuse. So 0.62 squared plus 2.02 squared, square root all of that, you're going to get a total distance of the center of mass is going to be equal to 2.11 meters from the origin.